Order creation latency spiked from 20 ms to 12 seconds. The checkout API returned 504 gateway timeout errors. One shard hit 95% CPU while others idled at 15%. The root cause? Sequential customer IDs from signup all landed in the last shard, and during a flash sale, new users overloaded it. Here's exactly why. Let's start with the basics of database sharding. Welcome to TheCodeForge. Before we dig into that production issue, let's cover database sharding. Sharding works by applying a sharding function to a chosen shard key, usually a column like userid or orderid, to determine which shard stores each row. The two dominant strategies are hash sharding and range sharding. Hash sharding applies a hash function to the shard key and takes modulo the number of shards. It distributes rows evenly, preventing hot shards. Range sharding assigns contiguous key ranges to each shard, which supports range queries but creates hot shards when sequential IDs cluster writes on a single shard. Here's a simple hash shard router that uses modulo and a range shard router that checks boundaries. Notice how the range router sends all sequential IDs to the last shard. Choosing the right shard key is the hardest part of sharding. A good shard key has high cardinality, uniform access patterns, and supports your query patterns. Common mistakes include sharding on created at or country. A lookup table decouples routing from the key value, allowing you to change shards without modifying the key. However, the lookup becomes a potential bottleneck. When a query doesn't include the shard key, the system must broadcast it to all shards and merge results. This is slow. Distributed transactions require coordination and are best avoided. For cross-shard transactions, the saga pattern breaks a transaction into local steps with compensating actions. If a step fails, it rolls back previous steps. Resharding is the most painful operation. With simple modulo, adding a shard remaps nearly all rows. Consistent hashing reduces this to only adjacent data. Consistent hashing maps data to a ring of hash values. When a new node is added, only data from its immediate neighbor moves. Before sharding, consider vertical scaling and read replicas. Sharding adds operational complexity that is rarely justified for data sets under 10 TB or write throughput under 10K writes second. This simple function captures the decision tree. Most applications never need sharding, optimize indexes, add caching, and scale vertically first. Directory-based sharding uses a lookup table that maps each entity to a shard. This decouples the shard key from the physical shard, allowing you to reassign shards without touching the data. This directory router uses RIDs to store the mapping. It assigns new entities to the least loaded shard. The lookup table must be highly available. Read-through caching with a distributed cache like RIDs can reduce database load by 60–80%. On cache miss, fetch from the correct shard, populate cache, and return. This Java code shows the read-through pattern. Check cache first, on misfetch from shard, then populate cache with a TTL. Always set a TTL to avoid stale data. This is the same issue we highlighted at the start. Here's exactly why that happened. The sign-up flow generated sequential IDs. During a flash sale, most orders came from new users, all hitting the same shard. The range shard router sent all new IDs to the last shard, causing 95% CPU and 12-second latency. The fix was to switch to hash sharding on customerid using modulo 8. They migrated existing data using a double write strategy. Write to both old and new shards for a week, then cut over. Now writes are evenly distributed. If a query doesn't include the shard key, the router must broadcast to all shards, causing high CPU and slow response times. Sharding on a column with few distinct values, like country, means most data goes to a few shards, defeating the purpose of sharding. This range shard router sends all sequential IDs to the last shard. During a flash sale, that shard becomes a bottleneck while others sit idle. The article's hashlib, MD5-based modulo routing is illustrative but not suitable for production. Python's hashlib MD5 is not guaranteed to be consistent across interpreter versions or platforms. For production, use a well-vetted consistent hashing library like hashring or pymemcache, hashring, or implement the hashlib, SHA-256, approach shown in the Java snippet. The article mentions consistent hashing, but only shows a basic ring without virtual nodes. Virtual nodes, vNodes, improve load distribution by mapping each physical node to multiple points on the ring. Here's a Python implementation using hashlib, MD5 for demonstration. In production, use a library like hashring. The article correctly warns against sequential IDs, but doesn't emphasize that even non-sequential IDs can cause hot shards if they are correlated, e.g., UUID v1 includes timestamp. Use UUID v7, time-ordered but random, or snowflake IDs that embed a random component to ensure uniform distribution across shards. The article mentions monitoring per shard load, but doesn't specify actionable thresholds. Set alerts when any shard's CPU or IOPS exceeds 150% of the average across all shards. Also monitor the number of connections per shard. A sudden spike may indicate a routing bug or a hot shard forming. To diagnose sharding issues, first check if queries include the shard key. Monitor per shard CPU and disk usage. Compute shard key distribution to detect skew. Use router logs to trace specific queries. Let's run through some common interview questions. What is a shard key and how do you choose one? High cardinality, even distribution, present in queries. What is the hot shard problem? Uneven load due to poor shard key. Prevent with hash sharding. How does consistent hashing help resharding? Minimizes data movement when removing nodes. And a few frequently asked questions. How do distributed transactions work in sharding? Use 2PC or Saga patterns, prefer data locality. What is resharding? Changing number of shards, consistent hashing reduces migration. Can I shard by a low-cardinality column? Technically yes, but leads to hot shards. To recap, always include the shard key in queries. Use hash sharding to avoid hot shards. Design for data locality to minimize cross-shard operations. And remember, most apps don't need sharding. Optimize indexes and scale vertically first. Ready to go deeper? Up next, database indexing, then normalization versus denormalization, then acid versus base. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.